Thank you and welcome back, everyone. So today I will focus on deep learning and, time permitting, also speak about generative learning at the end. And yeah, like last time, just raise your hand, ask questions whenever something is not clear. All right. And I will be skipping over a couple of slides because I'm kind of assembling one talk out of two on the spot. So don't be surprised if I'm just moving past a few slides. All right, so let's start with feed-forward neural networks. So first of all, yeah, what are neural networks? Neural networks are designed based on the idea that they are mimicking some sort of neuronal system similar to neuronal system in brains, human brains maybe. And brains, neurons in organisms are extremely complex, and there are actually many types of neurons that behave quite differently. But roughly, most neurons do signal processing in the sense that they have dendrites. So those are basically inputs. And then these inputs are somehow weighted, so they count differently much. And summed up. So there's basically electrical potential that is accumulated as a result of whatever arrives at the inputs. And then there is some sort of activation barrier. And if that activation barrier is passed, the neuron will send a signal to its outputs. And based on this idea, we put this very simple mathematical model for artificial neuron forward. And this is basically just inputs. These inputs are weighted. And we then sum them up and go into an activation function. So we can just write this as a scalar product of the input vector and the weight vector. And we apply this activation function, and we usually just write it like this. Of course, okay, so yeah, so in this case, it's just one neuron, so it's just one scalar. But even if we have many neurons, we would just write a function of the vector that goes, that is the input to all of these neurons in that layer. And then the idea is that we read these operations element-wise. So we will apply these functions element-wise. Okay, so every function is just the activation function of one neuron. There is usually one node, which is a bias node. So basically we learn something like WX plus B bias, and we can also alternatively write this bias by just clamping one input to 1, and then this weight here, W0, has the role of a bias. So the bias is basically just lowering or increasing the activation barrier, if you like. Okay. So these are inputs, bias nodes, weights. We sum up the signal and we have a nonlinear activation function. It's important for this to be nonlinear, otherwise there's not much use of putting multiple neurons behind each other subsequently. There are different types of activation functions. Traditionally, activation functions like logistic functions or hyperbolic tangent were used a lot. And those have fallen a little bit out of favor in the last couple of years. And a reason for this is that these activation functions, if you stack them very deep, so if you have many layers, have a problem with vanishing gradients. So because these signals saturate at large or small values, the gradient goes towards 0 for large and small values. And then it's very probable, if you have deep functions using these activation functions, that your gradient becomes very small. Your gradient information becomes very small. And then it becomes extremely hard to train the network. So deep neural networks basically couldn't be trained until something like 2006, 2009 maybe. And this year some advances, some methodological advances were made that helped us to train deeper neural networks. One important contribution was the use of rectified linear units, very simple activation functions. That's basically just the maximum of 0 and x. So it doesn't have a smooth derivative. It's just basically 0 for negative values and then linear for positive values. Obviously, there is a problem if you're always in the negative range, because then you always output 0 and your gradient is also 0. But in practice, if you have enough neurons, this is not a problem. It can be a problem if you don't have enough neurons. If for some reason all of the neurons in one layer are in this regime, then your network can basically break down. But statistically, it's typically not a problem if you initialize the network well. There are also other versions of rectified linear units which have some gradient information left of 0, like exponential linear units or soft plus functions. And those have also nicer behaved derivatives. But the idea is similar. Okay, so these have been used a lot in the past, and these ReLUs are used a lot more recently. Now, the simplest neural network that you can think of is a single neuron. If you define a single neuron and you define such a simple switching function as the activation function, this is called a perceptron. And a perceptron is basically, there's a training algorithm for the perceptron. That's not so important now, but a perceptron is doing basically, it learns a linear separation of its input space. It's a classifier that can classify into 2 classes. And it learns to do that by learning to place a separatrix, a linear separatrix in your input space. So with this, you can learn linearly separable functions. Like if you think about logical functions, where you want to predict which combination of 2 inputs gives you a 0 and a 1 as an output, you can learn an AND and an OR, because that's linearly separable. But an exclusive OR cannot be linearly separated. You would need 2 separation, 2 separatrices in order to represent the XOR. So what can we do? We can use deeper networks. We can use more than 1 neuron, and we can stack them. So then we have what's usually called a multi-layer perceptron. A multi-layer perceptron is simply a network with multiple layers with no particular structure. So often these networks are fully connected. So that means every network has a connection to, every neuron has a connection to every neuron in the preceding and in the next layer. So that's called a dense neural network, because we can represent the connectivities with a matrix for each layer. Where let's say the rows are for the incoming and the columns are for the outgoing neurons, and then we have a weight matrix, and these weight matrices are dense matrices, therefore dense neural networks. We usually count, when we're talking about layers, we usually count everything except for the input layers. So the inputs are just representing our input variables. Then we have some weights from the input variables to the first hidden layer. And then hidden layers and output layers are counted as layers. So this would be a 3-layer neural network. Okay, how do we train a multi-layer neural network? So neural networks are usually trained with some form of gradient descent. So we define a loss function. Like last time we talked about regression, and we defined the mean square error as a loss function that we want to minimize. And for training a neural network, we will also usually define a loss function, some function that we want to minimize. And we usually use some form of gradient descent. So we compute a gradient of the loss with respect to the parameters of the neural network. And then we change the parameters so as to minimize the loss. Now, this is a function. This is a function of functions of functions, because it's a multi-layer function. So we need basically the chain rule of differentiation here in order to compute derivatives. And because it would be very cumbersome to code up the derivatives, the analytical derivatives for every function that we define by building a neural network, it's very important to have an automatic way of computing these derivatives. And for neural networks, the way to do this is the backpropagation algorithm. It is basically just sort of an algorithmic convention to execute the chain rule of this differentiation for these neural network architectures. And the way it works is we first define, so we first have the loss function at the output, or the error function that we want to minimize. So we have some target values here, and we have the values that our network predicts, and this is some mean square error loss. And then we compute first the sensitivity of the error with respect to the activations of the output neurons. And then we backpropagate the sensitivity to preceding layers. So we basically always need to compute a derivative through the nonlinear function that is in every layer. So the activation function, but that is usually something we can just code, store and code once, because we have a certain set of activation functions that we choose from. So it's something that's easy to implement in neural network packages and just have it available. And then we pass these sensitivities on through the different layers. And using these sensitivities, they're also called error vectors, which is a bit of a misnomer, I think, but anyway, that's what it's called in the backpropagation algorithm, are then used to compute the derivatives of the error function with respect to the neural network weights. And once we have this, we can execute our gradient descent step. So now we can say we make an update of the weight in the negative direction of its gradient entry. Yeah, so that would be straightforward gradient descent. Now, if you ask yourself what is a neural network learning in terms of classification, what you can think about that it's kind of adapting its weights to learn to place a separation function through the input space, which might be very nonlinear at the input space. And of course, eventually the neural network does this by going through many layers. Yeah, the function that we're learning might be very nonlinear here in this space at the input space. And then we have all of these transformations to basically try to make the function that we are learning easier. In the end, of course, when you look at the last layer, what's happening here is that you're just doing some classification, if it's a classifier, or some regression, if you're doing a regression task. And of course, in the last layer, it's always linear, because you're learning a linear transformation of the previous neural network layer to your output neurons. So this is a linear operation. But then you go through a nonlinearity here, and then it's again a linear operation, nonlinearity, linear, etc., etc. So the idea is that these successive transformations make this initially extremely nonlinear problem successively easier. And in the end, you have a representation of your problem or of your input space, which can be linearly separated. Whereas in shallow learning algorithms, you try to directly find this linear separation, either in the input space or in the space that has been featurized, either by your handcrafted features or by a kernel method. Okay, what kind of functions can we learn with a neural network? What kind of functions can a neural network represent? So there's this universal representation theorem, which is very important from a, I would say, theoretical and philosophical point of view. It's less important from a practical point of view, because it tells us what a neural network can represent. It doesn't tell us how to do that. So a neural network with a single hidden layer can represent any, and here I'm simplifying a lot. Really, I should say any smooth function on a compact set, but I've omitted these details, with arbitrary precision, so to a precision level that we can define, so an error tolerance that we can accept, in the limit of having a large hidden layer. So that means single hidden layer, that means one input layer, one hidden layer, one output layer. So it's a two-layer neural network. The input and the output size are fixed by our problem definition, of course, but the number of hidden neurons is something that we consider variable. And the statement is, if we want to achieve a certain accuracy for representing a function, an input-output function, then we can do that with a two-layer neural network if we just have enough hidden neurons. The problem with this is we cannot necessarily show that we can learn this function. That's a completely different problem, how to find this function. So it may be theoretically possible to represent this function, but how to find the parameters for this function, that's an entirely different issue. Also, since this statement doesn't tell us anything about how many hidden neurons we might need to achieve a certain accuracy. And it can actually be shown for certain functions, so for certain problems, it can be mathematically shown that you need exponentially many hidden neurons in the input size, so in the input dimension, in order to achieve a certain fixed error bound. And then, of course, this is not a very useful theorem because we are interested in finding somehow a compact or an efficient representation. And it can also be shown for some of these functions that have these pathologies that deep neural networks can represent them with qualitatively fewer neurons, so with a number of neurons per layer that doesn't grow exponential in the input size. And this is because deep neural networks can somehow, through their depth, since they can represent functions of functions of functions of functions, they can represent hierarchical information, they can represent multi-scale information, which might be very hard to encode in a shallow way. Okay, so that's in some sense the theoretical justification why deep neural networks can be useful. There was a question, Benjamin.
Okay, so on that first slide, you might come to this, but it's sort of just thinking on the fly here. On the prior slide, it seems to me there are many applications. It matters what are X that one actually is interested in. So in most applications, one is not interested in approximating that function capital F for all X, but for a very, very sparse set or something. For example, for images, right? You don't want to learn something on a random pixel image or something. You only have a very, very small set, and one never cares about F being approximated on some very nicely behaved set of X values, but a very, very complicated set that one oftentimes cannot classify a priori. So how does that fit into that framework here?
So the statement is actually that this approximation is made on a compact set anyway, so it has to be somehow restricted. We cannot, if we allow to use the whole vector space, then it's not possible to bound the error at the same time. But this, as far as I'm aware, there is no theorem available that makes a statement for about particular sizes of input of manifolds at the input. And of course, in practice, as you say, we are interested to learn things on certain manifolds.
Okay. Yeah.
Yeah.
Right. Thank you.
So, okay, how should we think about what the neural network learns, or what its neurons actually represent? So we can think about the individual neurons to be something like feature detectors. So let's ask the question, what does a particular hidden neuron learn? And so we can basically say, okay, neuron, the first layer will be connected to the input image, so the pixels of an input image, let's say. And in this example, this neuron has a strong connection to the pixels in the first row and weak connections to the other pixels. So basically, it detects if there is a horizontal line here in the first row and ignores everything else. And then this neuron might be detecting patterns in the top left corner, etc. And so in a very naive view, you can say, all right, then there are certain features, if I want to detect, let's say, images or classify images of digits, then there are certain features like horizontal lines, small circles, etc., that I can define feature detectors for and learn them. But of course, this has several disadvantages. This view, for example, if I want to learn to detect a small circle, it doesn't make too much sense to encode this for every possible positioning of a small circle in the image. I want to generalize it a bit more. I want to maybe encode something like, is there a small circle somewhere, or is there a small circle in the lower half of the image, or something like this, and then combine this information with other features in order to decide what digit it is. All right, and in order to do this, it's very useful to use deep networks, because in deep networks, I can abstract information. So even not talking about convolutional neural networks yet, which have a smarter way of doing this, just deep multi-layer perceptrons or multi-layer perceptrons, more than 2 layers, can already have some abstraction, because if I have, let's say, simple feature detectors at the input, like horizontal bar at row 1, row 2, row 3, I can aggregate this information in another neuron that detects, is there any horizontal bar here? So in this way, I can already express higher level information in deeper layers. So multiple layers make sense from this point of view. As I mentioned before, until recently, deep neural networks could not be, not that recently, but maybe 10 years ago, couldn't be efficiently trained. So they weren't used much before a decade. And then a couple of people made very important contributions in making deep neural networks trainable, especially these 3 guys, Geoff Hinton, Joshua Benjo, and Jan LeCun, who is also in the advisory board of IPAM, are credited to have made very important contributions to making deep learning work. There's also another name, or 2 names that we should mention here, and that's Sepp Hochreiter and Jürgen Schmidhuber, who have invented the long short time memory, LSTM, which is actually something that was used for sequential information and time information mostly, but it's in some sense, it's an early incarnation of something called residual neural network, something that was rediscovered much later to train deep feed-forward neural networks. And I might come back to that. But before, let me ask if there are any questions up to this point.
So if you can go back to the slide where you were talking about the backpropagation, I have a question about how will the weights be modified in the second hidden layer?
So yeah, I mean the point, the purpose of backpropagation is basically to compute the derivative of the loss function with respect to every single weight. So that's this here. The E is the error function here, or loss function, with respect to WJI. That's the weight in layer J neuron I, or the other way around.
So what will be the error for the second one? Because what will be the DJ at that point? So,
sorry, the DG, where's DG?
That in the definition of E, you have a DJ, right? So this is the...
Okay, so this is, so here I'm assuming I'm just doing supervised learning, and one of the 2, I believe, Y. Yeah, Y are the output activations. So those are the neural network outputs, and DG in this case is just the label that I'm training against. So this defines the error that I'm making at the output. That's the derivative. And here I'm just backpropagating the derivatives to previous layers. And then I'm eventually computing the derivative of the loss function with respect to every single weight.
Okay.
And then I'm making a weight update.
Yeah, thank you.
Okay.
Makes sense.
You're welcome. So ultimately, this is just the chain rule, really. It's just essentially an automating the chain rule. Okay, so let me come to convolutional neural networks. So convolutional neural networks, or some form of convolution, is basically still the state of the art for any kind of image processing or any kind of processing of data that has a regular topological structure, where the individual dimensions of the data are somehow have a fixed relationship to the other dimensions, such as the pixels in an image have neighbor pixels, and there's a good reason to somehow use this information, to use this neighborhood information. And yeah, convolutional neural networks traditionally consist of convolutions of some form of subsampling or pooling to make the results of the convolution smaller. And then often we have dense neural networks, so multi-layer perceptrons, but not too deep usually at the output, to do, for example, a classification task. And convolutional neural networks were really pioneered by Yann LeCun. Lequin, I'm not even sure how to pronounce it. He's French, so Lequin, I guess, is the right way to do it. So what's the idea here? So the core idea is really to use convolutions. So I'm just showing you a discrete convolution here. And the idea here is that we have an image. This is shown in blue here, and the numbers here are just the pixel intensities, so the activation of the input neurons, if you like. And the gray box here, that's the convolutional kernel. So that's basically the second signal. So I'm convolving two signals with each other. And what I'm doing during the convolution is that I shift one signal across the other one. So I position this gray box in different places of the blue box. And then I'm basically computing the scalar product of the overlapping entries. Yeah, so here I have 332.001.312 from the blue signal, and I have 0.122.20.012 from the gray signal. So I can say these are two vectors, and I compute the scalar product between them. So 3 times 0 plus 3 times 1, etc. And then I get 12 when I execute this. Then I shift my gray image to the next position. I also get 12. I shift it again. I get 17, etc., etc. So that's the discrete convolution. And here I have respected boundary conditions. So I haven't put the gray box anywhere outside the blue box. So my convolved image is smaller than the original image because of this boundary effect. But I could use different definitions of how I treat the boundary. So for example, what's often done is so-called zero padding. So I just augment one of my signals with zeros. And then I can also go outside the boundary of my original image, and then I can ensure that, for example, my output image has the same size as the input image, and that's sometimes desired. For example, when I want to make very deep convolutional networks, residual neural networks with convolutions, for example, then I don't want this effect that my image becomes smaller with every convolution, because otherwise I just lose my signal at some point as a result of this boundary effect. And then I usually use zero padding. Okay. So then we have other elements in a convolutional neural network. So we may have subsample layers or pooling layers. that essentially make the signal smaller. So for example, I may just take every second or every fourth pixel, or I define a neighborhood like a 2 by 2 pixel neighborhood and take the maximum pixel from there. And the idea there is if I'm doing something like classification in the end, I'm basically looking for features and I just want to know, has a certain feature come up in a certain environment? And then I just take the max to pass this information on and I throw the non-max entries away. And then usually in the end, as I said, I have a fully connected layer. If I want to use this network, for example, for classification or for regression or something like that. Okay, convolutions. So these convolutional filters. So of course, convolution is nothing new or nothing recent. So convolutions have been used for a very long time in signal processing. And actually they're used a lot in image processing softwares such as Photoshop or Lightroom. And usually the type of convolutions that are used there are just fixed convolutions. So the convolutional kernel is somehow fixed and has a certain effect on the image. For example, it may highlight the edges of an image or sharpen the image or introduce a blur or something like this. So there are certain convolutional kernels that have certain optical effects on the image, like this. And the idea of a convolutional neural network is now to learn these elements. So these elements of the convolutional kernel, these are our weights. All right, so what has been the weights on the edges of the densely connected network before, now is the elements in these convolutional kernels. And we can actually show in a very simple way that a convolutional neural network is a special case of a dense neural network. We can write what a dense neural network does. Let me go back to the. Oh, wow, I have to go back quite a bit. Sorry. Okay, we can write what a dense. Let's say we start with these inputs. So we can write these inputs as a vector. In this case, with 3 elements. The output. So the input to the next layer is a vector with 5 elements. So now we can write a matrix 3 by 5, which takes these inputs and moves it to the output. And then if I'm going through a nonlinearity, so in the next layer, what I'm doing is I'm basically taking the input vector, apply the weight matrix. Then I have the vector that goes into my nonlinear functions, and then I apply the function to the resulting vector, and that's my input to the next layer. Okay, so this matrix, this weight matrix, this tells me what are the weights at all of these edges here. But it also tells me something about the structure of what's connected to what, because whenever there's a 0, that basically means there's no connection. Now in a convolutional neural network, that's exactly the same, just that in a convolutional layer, I have mostly zeros. I, in fact, have something that's called triplets matrix. So a matrix where certain weights will show up in every row, basically just shifted, so at different column positions. So a convolutional neural network is a special dense neural network. All right, so it's strictly less powerful if I'm just talking about expressivity of what the function can express. So I must have a good reason for using a convolutional layer instead of a dense layer. Okay, and this good reason for images is that I'm interested in something like translational invariance or translational equivariance. What does that mean? So if I am detecting a llama in my image, oh, this is actually not a llama, I think it's a rat or something like that. Okay, so let's say a rat, or a cat because it's more cute, then it doesn't matter if this cat is in the top left or in the bottom right of my image. I want to be able to learn this only once. It shouldn't matter.
I think Benny has a question.
Sure, please.
Just for clarification, so the turbulent structure is one restriction that one puts by having the same filter everywhere. But are you also restricting explicitly that what is nearby each other in the signal, or are you allowing the filter to be non-locally in the pixel domains a priori, and then allow complete freedom to learn that? So do you also restrict that a priori, the locality and what is nearby as well?
Yes, so you define a filter size or kernel size, and that is in the matrix is expressed by the zeros that are in each row.
So you're explicitly encoding proximity, right? If I were to reshuffle my pixels a priori, which is the same problem, right? Just reshuffled, a convolutional network would give me a different solution. It would be different.
Yes, absolutely.
Okay, so then it seems like this is obviously a good idea for images, but it's unclear why this would be a good idea for other applications.
Yeah, I mean, it really relies on your signal to come from some sort of physical space, I would say, either space or time, or so that there's some ordering in your dimensions. Absolutely.
But whenever one has a notion of proximity somehow, then these convolutional networks always work well, or is that generally observed, or is it that there's something special about image that goes beyond the notion of proximity?
So yes, I would say it always makes sense to somehow encode proximity. So any topological information about your signal that you have. In machine learning, this is so, as I said, in terms of what functions can you represent? This is a restriction, right? You're reducing the set of functions that you can learn. And this is machine learning is called inductive bias. You have some knowledge about the structure of your functions that you want to represent, and it makes sense to reduce the search for functions to that state.
So if you had a super powerful optimizer that could just exhaustively search everything, you could not do that restriction and find the same solution, potentially. But a priori, you know that this is probably good, so you make it easier on yourself.
Well, having a good optimizer is not enough. You have to have enough data to learn all of these parameters. That's the main bottleneck.
Okay, great. Thank you.
There's another question from Darius.
Okay. There's one more question. The locality due to your kernel basically is one of the reasons why all the adversarial attacks work. So you know that there are many examples where people are modifying the images to let something look like something else just by adding a feature close to the region, which confuses the network. Just because the network is not looking at the entire image, it's just looking always at a small region, and it's concatenating the responses. So there are a lot of examples where speed limits are basically getting completely fooled because you just add a small line somewhere and suddenly the network responds differently just because you have this locality. So the full network gives you a full analysis of the image. Your convolutional networks just assembles local responses.
Yes, that's true, but one somehow has to deal with that differently because I mean, training image problems with dense neural networks is basically not really an option. If you think about having a 1000 by 1000 pixel input, that would mean 1 million neurons. If you had a densely connected neural network and the next layer also has something like 1 million neurons, then you have a problem because then you have a weight matrix 1 million by 1 million. So that's not trainable and not storable. So one somehow has to use this locality, even for efficiency reasons. And then there are various regularization methods such as dropout or training with noise. There are adversarial training methods. So there's a whole research field basically about how can I deal with adversarial attacks. So that's a very important question in machine learning. And there are different types of adversarial attacks, right? There are kind of these simple problems with noise. If you just add Gaussian noise to the input, let's say, if you trained with a very well curated data set like MNIST or Cypher, and you just add a little bit of noise, you can quickly deteriorate the quality of your predictions. But this is something that can be relatively easily dealt with during training. But then there is also the more challenging problem of intentional attacks. So somebody is trying to make a small modification to your input that maximally screws up your output prediction. And so this is something that is much harder to safeguard.
Thank you.
So convolutional neural networks, because they have this learning of filter structure, so these filters are also very interesting to look at, and it reveals to some degree what kind of sort of how the information is stored in the convolutional neural networks. So very often, or almost exclusively, I would say, if you train the network on images, you get these edge detection filters in the first convolution layer, and other filters that find certain shape or color information. Just because detecting edges are almost exclusively useful when you want to detect some information in the image, some sort of object or so. Trained on a face database, and typically in the next layer, you'll see something like eyes, noses, etc. And in the next layer, maybe parts of faces or like these ghostly faces that are a little bit reminiscent of eigenfaces. If you do a principal component analysis on a face database, you get something like this. Another question.
Go ahead, please.
So in these images, so are these of the actual like convolutional filter?
Yep.
Just like plotted? So then in like the second and third layers, then it seems like the convolutions they're like much bigger, right?
Yes, they're kind of projected back to the input, I think. Yeah, so I'm not entirely sure now how this is done. I think this is somehow the field of view representation. I'm not exactly sure now how this deals with the pooling or the subsampling layer in this particular example. But the idea is like what is the activation at the input, which maximally activates this convolutional kernel in layer 1, 2, 3. That's what we're plotting here.
Okay, so it's not the actual like filter itself. It's something somehow like some more complicated.
It's a stack of filters.
Yeah, okay.
Mm-hmm. Yeah, thank you. Good point. Okay. I think I will switch talks now because I want to talk a little bit about generative learning. Okay. So I hope you can see the slides again. Yeah, seems to be the case. So let me talk about neural networks for generative learning. So this is an unsupervised learning task. So now we are not asking the question, how can we find a function to minimize a certain error given certain labels, for example, for classification or regression. But we just have data given from some space, and we want to be able to generate data from the same space. So mathematically, what we would like to do is we would like to learn the probability distribution of that data set, and we would like to be able to draw samples from it. And there's a whole zoo of generative models, and a classical example, a classical animal from the zoo is Boltzmann machines or restricted Boltzmann machines, which is a sampling method. So it uses Markov chain Monte Carlo in order to generate samples. But in the last couple of years, a more common or popular class of neural networks has become the directed generative nets. And the idea of directed generative nets is as follows. So we have a neural network, so some sort of trainable function. We have an input, which is basically random noise. So these are this is just some sample from a multivariate random variable that is easy to generate. For example, we just sample Gaussian pixel intensities at every pixel. So basically it just looks like one of these 1980 TV screens after 2 a.m. in the night that probably most of you have never encountered, but I'm sufficiently old to have seen them. And then we want to learn a transformation of those trivial random vectors, basically, or random arrays into something that we're interested in, such as images, faces of celebrities, for example, if that's something we're interested in. Okay, so that is the task. And then, of course, the question, how do we train this? Yeah, if we just have data, if we just have images from a database, how do we tell whether the network is improving in learning the distribution underlying this database? What does it even mean, this distribution? And yeah, so mainly, what is the learning principle behind this? But mathematically, the idea is somehow transformation of random variables. Yeah, so we have an input random variable from a simple attractable distribution. This input space now in generative nets is usually the latent space. So that's the space where we do simple things in some sense. And then we perform a transformation. So we learn a function which transforms these samples to the desired distribution. And this desired distribution can be more complex. And two famous architectures which are doing this are variational autoencoders and generative adversarial networks. And then there's a third class which is very popular, especially has become extremely popular in the last couple of years, and that is normalizing flows. And normalizing flows, I will not talk about that here. The idea of normalizing flows is to use a function g, so this transformation function, which is bijective. So it's an invertible function. We can compute the output for the input and the input for the output unambiguously. And if we have a bijective function and we apply it to a random variable, then we can use the transformation of random variables rule, and we can compute the probability distribution at the output of the function, given the probability distribution at the input, which is something that we know because it's a simple distribution at the input, and given the determinant of the Jacobian of the transformation. So the determinant of the matrix of the first derivatives of all outputs with respect to all inputs. So if our function g is such that this Jacobian can be efficiently computed, then we can compute this. And then we are able to compute the probability of the output distribution, and then we can do things like maximum likelihood, which is really nice. But this is a restriction, yeah, because I'm now restricting myself to invertible functions, and that's a much smaller set of functions than any function, any feed-forward function. So there's a price to pay for this. These approaches here, variational autoencoders and generative adversarial networks, do not do this. They do not ask for an invertible function. As a result, we also have no direct way to compute the probability of the output sample. We cannot use the transformation of random variables rule. So we need other principles than maximum likelihood to train our generative network. Okay, here's just a visualization of what's the type of thing we're doing. Let's say we start with a Gaussian distribution. We want to learn to sample points on a circle. And this is an example where we can learn a function that takes Gaussian random variables as an input and puts things on a circle at the output, at least approximately. Okay. So let me check the time. All right, a few minutes. So let me at least talk about generative adversarial networks. the idea of generative adversarial networks is that that's a quite unusual way of training a neural network, and that was also a really innovative idea in 2014 or 13 when they came up, and this paper is super highly cited. I think it has maybe 30,000 citations or something like this. And the idea is this is really a game between two networks. So we have two adversaries, two networks that play against each other: the generator network and the discriminator network. And these networks compete. So the generator network produces the sample. So this is really the network that takes our latent space samples, so let's say samples from Gaussian random variables, and tries to learn to produce outputs like images of celebrities, let's say, if that's our task, that are compelling. And the discriminator network wants to decide if the samples it receives are true samples, so if they were from our original database, or whether they were generated by the generator. So basically, the generator is trying to fool the discriminator, and the discriminator is trying to police the generator. And these two networks play a zero-sum game. So basically, we have a reward to give, and we give it either to the discriminator or to the generator, depending on who wins any time that this game is played. So when the discriminator detects correctly that the input was false or true, then it gets a reward. Whenever the generator manages to fool the discriminator into falsely believing that its output was a true sample, it gets a reward. And then the other network gets the corresponding penalty. So it's a zero-sum game. Only one of the two wins. Okay, so here's just a flowchart of how this works. So for a training set, I have examples of images or whatever I wanna be able to generate. Here I have random noise, so some samples from a simple distribution. I have the generator network, a feed-forward neural network, which produces images, fake images, and I have the discriminator, which just does basically two-class discrimination. Is the input real or is it fake? And then I'm training this. So because every network tries to maximize its own performance and minimize the other network's performance, is a min-max game. I'm not really looking for a global optimum, maximum or minimum of a loss function or reward function, but I'm looking for a saddle point. I'm looking for something which is maximal in one set of directions and minimal in another set of directions. And the different directions here correspond to the parameters of the generator and the parameters of the discriminator. And saddle points are harder to find than minima or maxima. So this is why these sort of networks are hard to train. And there's a lot of research on how to make it easier trainable, to avoid things like mode collapse. Situations where we always generate the same boring kind of stuff that looks good but doesn't have any variety in it, etc. And I just want to show you a few examples. So this is an old example, but I still find it quite compelling. So this is now after a generative adversarial network has been trained. We are working in latent space, and we do the following. We do arithmetic operations in latent space vectors. So we take images of, let's say, men with glasses. So these are latent space vectors that encode things that look like men with glasses. They don't look very good, but in terms of there are many like pixel errors, etc. But this is an old example. But I think you get the point. So these are men with glasses. We take latent space vectors of men without glasses, and we take latent space vectors of women without classes. And then we take men with glasses minus men without glasses plus women without glasses. We literally do minus plus in these vectors. And then we have a resulting vector. We push it through the generator and we get a woman with glasses. Yeah, and you can imagine that doing something like this is completely meaningless in pixel space. So the network learns some sort of meaningful, simplified representation in its latent space. So these kind of tricks people like to play in latent spaces of generative models. Ronan.
What exactly do you mean by latent space, and how would you compute such a thing?
It's this space. So it's just a space in which I'm generating my random inputs. Now can I of course take some vector in this space, so some input, and ask what is its corresponding output. Yeah, what does this generator network do with a certain input vector? So here I'm taking a latent space array which maps to this image, which is a man with glasses. Same here, same here. And here I take latent space vectors or arrays that are corresponding to man without glasses if I push them through the generator, etc. And I'm doing these arithmetic operations in the latent space, so before pushing it through the generator. Is it clear?
Yeah, that makes sense. But I have another question, which is, so when you generate like this random vector that you feed to the network, will you just get, like, how do you control whether that will correspond to a man with glasses or a man without glasses?
Oh, here I'm just selecting something, right? I could take, basically take a certain output that I want to have, and then search over inputs and try to find something which generates this output. I mean, this is just essentially to make this point here, that I can do something like simple arithmetic operations at the input. Or I could do things like interpolations. I can take 2 points that correspond to something different at the output, do a linear interpolation in this latent space, and then I get sort of like a morph at the output space between two faces.
Okay.
But the interesting thing is that this morph, like essentially every image along the morph looks like a face. So none of them would look really like a completely nonsense image.
Okay, I see.
There is another question from Tanushree.
So, am I right to believe that the other network, the discriminator, has as its training a woman with glasses?
Say that again, I didn't.
So the discriminator, so what is the input to the discriminator? Is it like women with glasses? That will be the training set?
So the input to the discriminator is an image that has either been generated by the generator or is in the training set. So when I'm training this neural network, I'm taking all the images that I have. Let's say for the celebrity problem, there is a celebrity data set with, I don't know, 100,000 photos of celebrities. So that's my training set. And then what I would do is I would take samples from this data set, and I would also produce samples from my generator, which are generated randomly. I generate random noise at the input, push it through the generator, get images. And then I present those to this discriminator without telling the discriminator which one it is. And then I'm just training the discriminator on increasing its probability to make the right decision. Then next, I would train the generator. I keep the discriminator fixed, so the discriminator variable is fixed, then I'm training the generator. So I'm doing the same, pull data from my training set, generate random noise at the input, go through the entire pipeline. My discriminator says real or fake. And then whenever the discriminator is wrong, then the generator gets a reward.
So how is this this decision being made, whether it's real or fake? Like, how is that decision made?
It's only made at the training, because at the training, I know whether it was a real or a fake sample. So it's like a label. I can assign a label. And then later, when I use the generator, so the discriminator is not needed anymore at the end. At the end, I just want to use my generator.
Okay.
Then I just input random noise or whatever I want, and I generate images.
So for this example with the woman with glasses, what will be the, so when you're saying real or fake, it is if the picture formed has glasses, then it is real. And if the picture form does not have a glass, it will be fake.
So this is not an example of real or fake. I mean, in some sense, these are all fake because they are outputs of the generator. This just shows that the generator has learned a structure in which I can do complicated operations on images in a simple way by doing these operations in the latent space. So beyond being able to sample images, I have learned a simple representation of the manifold of images so that I can do simple things with it at the input, like interpolation or addition, subtraction, things like that.
Thank you so much.
Okay, Frank, if you want to wrap up, I think we still have little time for additional questions.
Yeah, let me do that. And let me just go through another example. This is a very important paper by NVIDIA of 2018. And basically, this is sort of a multi-scale approach to train these GANs, where I subsample the image. So I start with a large image, and then I make it successively smaller and smaller. And I'm first training my GAN on these small images. So I'm training it on 4x4 images and training the generator to generate 4x4 images, because that's much easier than training a generator in a very high dimensional space. So until 2018 was basically not possible to generate high resolution images with any of these techniques that looked good. And so what they did was to do this like successive training on differently coarse-grained versions of the image. And then this here is the output of such generator. So this is trained on a CellApp-A data set, so an image data set of celebrities. And these are all completely made up generated images by the generator. So none of these people are real. They just look important. So the network has learned something about celebrities, but they're completely generated, right? And this is 1024 by 1024. So now they can do 4096 by 4096 super resolution, and it looks super impressive. So check out StyleGAN or StyleGAN 2 by NVIDIA. So I think they also have an interactive app on the website that you can play with, where you can like morph between images and generate things around phases that you start with, etc. But it works very well if the data set that you are training on is not too wide or has too much variation. So faces, for example, is something that works really well, probably because the underlying manifold behind faces is maybe not that high. There's a lot of similarities between faces. Like people have usually two eyes and one nose and one mouth, and also these faces are usually aligned, like people look kind of towards the camera. But it's much harder to generate something like reasonable images of planes that don't fall apart, as you see here. That's using the same system. And of course, it's obvious that it's very difficult to do something like this without kind of encoding or understanding something about physics or engineering, or some sort of knowledge that if I want to generate a plane, it should be like a contiguous object and not in pieces and things like that. So probably you need a lot more structure in your neural network to do this. Okay, so this is enough for today, I would say. So I'm wrapping up.